Oh, it's been my pleasure to work with Stella, Kaitlin, Sarah, Eric, and John on this Chapter 8 for Protostars and Planet 7. Three of us were able to make it in person, Stella, myself, and John, and just to help with recognizing us in the poster sessions. That should help a little bit. So just some basic background. Most bright stars in the night sky are members of multiples. Springtime, my favorite asterism is the Big Dipper. I found out recently here in Japan, they usually call it the Northern Dipper. And 6 of those 7 stars are actually members of multiples. In fact, you can see Mizar and Alcor here is the 2nd star in the handle of the Big Dipper. You can split it with your naked eye into a binary. But Mizar itself is a double-double quadruple, where you have the outer pair separated by 15 arc seconds, and then each of those pairs gets resolved into a pair of spectroscopic binaries, orbital periods of tens of hundreds of days. And Alcor itself is a binary, has an early M companion recently discovered with adaptive optics. So Mizar and Alcor actually form a sextuple system. There's several sextuple systems and actually a couple septuple systems we know about. And then there's other binary multiples among the Big Dipper asterism. And you need a variety of detection techniques to probe the different binary separations and brightness contrast. So this one was found with astrometry, this one was visually resolved. And so the fact that most of these bright stars we see in the sky, night sky, are multiples, really cannot ignore binaries in the context of star and planet formation. One main thing to emphasize is it's been a decade since PP6. I'd say there's 4 main categories, main advances that has really helped our understanding of multiplicity. One is Gaia. The first 2 in early data release 3 found millions of these resolved visual binaries. In the past year, we now have the full data release 3 with astrometric, eclipsing, and spectroscopic binaries. Another advance has been this time domain survey, these like SDSS apogee, where you get multi-epoch, high-resolution spectra of hundreds of thousands of stars. And not only can we find these spectroscopic binaries, but we can measure their chemical abundances and probe binaries as a function of different environments and metallicity. As you go toward longer wavelengths, ALMA has really been able to resolve the gas and disk structure of protostellar disks, not only in single stars, but also in binaries, so you can compare the disk structures of binaries versus single stars. And also there's been advances in numerical simulations, higher resolution, but also new and improved physics, MHD, radiation, and various feedback processes like outflows, supernovae, and jets. So the outline of this talk in the chapter is really comparing observations and theory of multiple star formation. I might break it up into 5 parameters. Hopefully we can all keep track of 5 parameters. On one hand, how does binary multiplicity depend on stellar mass, the orbital separation, age, or the class, 0, 1, 2, or 3. When I say cluster/slash association, so I don't get in trouble here, the density of their environment, and also the metallicity of the stars. And at the very end, I have a few slides about highlighting the impact of binaries on planet formation. So this is one of the first figure in our paper here. Each of those data points comes from several to maybe a dozen different surveys. Overall, we did a meta-analysis of 50 different surveys. So please look at the chapter. Overall, we have about 300 citations if you want to get the full references. So right here, we're plotting the multiplicity fraction as a function of primary mass. About half of stars like our sun are in binaries. As you go lower mass, M dwarfs down to brown dwarfs, binary fraction, the multiplicity fraction decreases. And then as you go higher in mass, basically all O and B stars have at least one companion. That's the overall multiplicity fraction. We now have measurements of the triple star fraction, or higher order multiples. About 15% of solar mass stars are in triples. And again, this goes in mass, increases in mass. And so most OB stars are not in binaries. Most OB stars are in triples and higher order multiples. This is a similar graph showing the companion frequency, where now we're saying, okay, what is the mean number of companions per primary? So the average solar type star has about 0.6, 0.7 companions per primary, but going back up to O stars, the average O star has 2.1 companions per primary. There are four main formation channels for multiple stars. I'm going to highlight each of these four separately with these three different diagrams here. On the top is just a cartoon illustration indicating the time scale and the length scale of these formation processes. Then we have an actual image, typically from ALMA, but also VLA, of these different snapshots where we can actually directly see these fragmentation processes occurring in nature. And then the bottom here, we have these theoretical numerical simulations. So I really enjoyed the talks this morning discussing filament fragmentation. And I just want to highlight here that if the filament has a critical mass, it will undergo fragmentation, like beads on a string. It will separate into these separate little cores here along the filament. Also on these very large separation scales, 10,000s, 100,000 AU, we can get core fragmentation. This is where subregions of the core gravitationally collapse because the gravitational energy exceeds the combined turbulent and thermal energy. And so it can be parameterized by this equation here. If the core reaches some critical density that depends on the central density, the radius of that core, and the Mach number, we can define this critical threshold for the core to undergo fragmentation. On smaller scales, now at separations of 10 to 500 AU, basically at the edges of these protostellar disks, you can get disk fragmentation. And so the main equation here is the tumor AQ parameter, and which can also be scaled in terms of the ratio of the star to disk mass ratio here and the aspect ratio. And the most important thing in this relation here is as the surface density or the mass of the disk goes up, or as the temperature, sound speed of the disk goes down, you are more prone to fragmentation. So just keep in mind those trends as we go forward for the rest of this talk. And the final mechanism of least dynamical decay is capture. So you can have two protostars with their disks. They're not gravitationally bound, but then there's some mediation of the gas or some kind of disk capture that causes them to become gravitationally bound. Again, I just love these simulations here by Diego, and then here's this actual observation again of these tidal tails here. I love, oh man, just look at this spiral structure of these gravitationally unstable disks there. And so yeah, I really want to highlight this is like only in this past decade have we able to directly observe the fragmentation processes, the formation of these multiples via these different formation channels. I'm now plotting the overall binary separation distribution as a function of stellar mass. You can see low mass binaries follow these log normal separation distribution. Solar type binaries peak about 50 AU. And then as you go lower in mass, they get concentrated towards shorter and shorter separations. All brown dwarf binaries are actually less than 10 AU. The orange figure here is showing that if you look at metal poor solar type stars, halo stars, they actually have a larger closed binary fraction. We'll come back to that in a little bit. But then as a function of mass, you can just see that the O-type stars have a very large multiplicity fraction. If you just integrate this histogram here, you get that result I mentioned. Most, on average, an O star has 2.1 companions per primary. But the inner binaries are really skewed towards short separations, indicated by this dotted line here. 70% of O stars have companions within 10 AU, really skewed towards these very short separations. A similar plot, but now looking at only solar type stars in young environments. For reference, I'm plotting the, in black here, the field, solar type field, FGK, main sequence population. And what Marina et al., Kunkel et al. Found is that you look at close separations, spectroscopic binaries, the close binary fraction of T-Tauri stars actually matches the field population. And really don't find any statistically significant dependence on the environment, the cluster age, or density. It's quite a bit of a different story for these wider binaries. You look at these class 0 objects, there's this large excess of these 1,000 AU plus binaries. And that goes down a little bit towards class 1. And the idea is that either these excess of wide binaries are just weakly gravitationally bound and get dynamically disrupted, or they actually migrate inward by the time you get to the T-Tauri class 2 phase. And so yeah, you can just see that dramatic excess of these wide class 0 binaries. Now let's look at cluster density. I'm going to focus on these 100 AU to 10,000 AU binaries. In low density regions like Taurus, there's actually this excess of these wide binaries. But in very dense regions like the central regions of the Orion Nebula Cluster, all the dynamical interactions disrupt these wide binaries. And so there's a dearth, a deficit of these wide binaries. And the intermediate density regions like Upper Scorpius actually matches the field population. And so there's a discussion of where do stars form and dense clusters, associations. What I can say is that Upper SCO represents the average environment where solar type stars form. That's because if solar types formed in low density environments like Taurus, we'd see this excess of wide binaries. Whereas if all solar type stars formed in Orion, we'd see this deficit of wide binaries. So we can actually use this dependence to actually measure what is the typical environment for the formation of solar type stars. It's a mixture of Orion nebulae cluster environments, Upper SCO and Taurus, that gives this average distribution that we now see in the field. Going to focus on the close binary fraction here for the next few slides. And we can see that by close binaries, I'm saying the bias corrected fraction below 10 AU. And for M dwarfs and brown dwarfs, it's about 15%, maybe for K dwarfs as well. But then starting around 1 solar mass, we start seeing this dramatic uptick in the close binary fraction of stars, scaling as mass to the 0.5 power. So we think that these low mass binaries come from core fragmentation. They don't have sufficient mass for the protostellar disks to become gravitationally unstable. But as you increase in mass of those protostellar disks, they're more likely to fragment and form these close binaries. Again, here's the 2 Murray cube parameter with the surface density of the disk in the denominator. More massive disks, more prone to fragmentation. But also these more massive disks have a lot of gas in it that can help dissipate the orbital energy of that companion. And so these more massive protostellar disks also aid in the inward migration of those proto-binaries. Andrei Tobin and I built on earlier work, and this is discussed in the chapter, of the overall evolution of disfragmentation, accretion, and migration. And so we think that gravitational instability occurs at the edge of the disk, so let's say about 200 AU. At the edge of the disk is where it's coolest, and therefore most prone to fragmentation, gravitational instability. And that initial fragment is very, very small. It's brown dwarfish mass. Extreme mass ratios is the initial, immediately after fragmentation of that disk. Because you have this low mass companion, it orbits in this wide radius, while the central protostar remains relatively stationary. And so as that companion clears a gap, and you have a circumbinary disk, most of the accretion falls onto that companion. You have preferential accretion onto the secondary. And the torques are such in this extreme mass ratio regime that you have inward migration as the binary accretes from a circumbinary disk. And so in the simulation here, you can see we start with these extreme mass ratio binaries at these wide separations, but over time they accrete and migrate inward. And so we actually reproduce this the observed excess twin fraction. About 30% of close solar type binaries are these twins here. And we can explain that with this physical process here. Meanwhile, we also get reproduced this brown dwarf desert. This was discovered back in the mid-aughts. It's very difficult to create brown dwarf companions that can migrate inward without also gaining in mass and becoming a stellar companion. And so we naturally reproduce this brown dwarf desert. We also reproduce the short period tail of the period distribution of solar type binaries. This red here is the overall separation distribution here, and our simulation is only modeling disk fragmentation binaries. So below 1 AU, we do a good job of matching observations. But beyond 1 AU, core fragmentation binaries are the main contributor to this overall shape of the period distribution. You need both disk fragmentation, these less than 1 AU separations, and then beyond that, you're really dominated by core fragmentation. So that's for solar type stars. We also cranked up the mass and looked at the differences for disk fragmentation of OB binaries. And by cranking up the mass, you're more prone to fragmentation, but you also yield this more efficient disk migration. And again, we fragment somewhere on these few hundred AU scales, migrate inward. And we actually, for these more massive close binaries, we find a more uniform distribution of mass ratios. That's actually consistent with observations, quite different than what we see for solar type binary mass ratios. And we reproduce what Sana et al. Found, this skewed distribution towards very short periods. 70% of OP stars have companions less than 10 to the 4 days, or A less than 10 AU, and it's very skewed towards short separations. Again, these more massive disks really aid in this inward migration. And then there's a cliff around 1 day. And that's the Roche limit of these pre-main sequence stars. So we actually predict that a sizable fraction of these companions actually migrated all the way in and merged. And these simulations for 10 solar mass stars is about 30%. But as you gain higher and higher in mass, you're more likely to form these pre-main sequence mergers. And these most massive stars, it's actually very difficult to, above 100 solar masses to form via gas accretion alone. They have to exceed their Eddington limit by several, almost an order of magnitude. And so the easier way to form these most massive stars is through these pre-main sequence binary mergers, where you have the inward migration inward, and then they just coalesce during the pre-main sequence. And again, here's one of my favorite movies of disk fragmentation, which we think is the dominant mode of fragmentation for close, massive binaries. For other types of binaries, it's a different story. And so it's really cool. You can see actually there's a forward of a triple there. Let me show it one more time there. This is the zoom in here and a large scale view there, top down view and the side view. You can see it opens up the cavity. You really see the spiral structure from the gravitationally unstable disk. And then after a while, settles down into two stable disks separated by a few hundred AU. Okay, so we're talking about close binaries. Let's go on to wide binaries. So now we're applying the wide binary fraction as a function of primary mass. And again, it also goes up with stellar mass, but for a completely different reason. We can see it goes up pretty steeply from 0.2 solar masses up to 10, 20 solar masses. But there's this dearth of late M brown dwarf binaries at wide separations. We don't see any wide brown dwarf or late M dwarf binaries. And there's three reasons for this. As we talked about, in order for a molecular core to fragment, you have to have a critical density threshold. And that's just not readily achieved in these low mass cores. So low mass cores are less likely to fragment. And when they do form, one of two things happens. Either they're dynamically disrupted, they have a lower binding energy, or because they have less inertia, they easily decay from these core fragmentation, filament fragmentation scales of 10,000 AU and decay via dynamical friction or disk capture onto these shorter separations of 100 AU. And I want to show a simulation of the latter there. Here's an orbital decay of these low mass binaries via dynamical friction and gas-mediated capture. Let me just back that up. So we start off with a single star there, and then you can see this flyby coming here, and then the interactions of the gas and the surrounding disk. Actually, there's really not really disk there. It is just dynamical friction. There's the disk coming in. You get decay orbital separations of 2 orders of magnitude on these very rapid timescales. And when you put all the physics together, these numerical simulations, for the past decade, the simulations have been able to reproduce the overall observed multiplicity fraction of main sequence stars, going from nearly 100% for OB stars down to 20% for these brown dwarfs. So I think it's really remarkable that over this large range of masses, by including all these physics and these numerical simulations, we can reproduce this overall trend. Okay, I have a few slides on the impact of metallicity on binary star formation. A couple years ago, Kaitlin, Kratter, Carlos Padenis, and I did a meta-analysis looking at how the close binary fraction depends on metallicity. So we're plotting here the bias-corrected solar type close binary fraction. Again, by close, I mean less than 10 AU. And all these different surveys, there's Carlos's paper, taking in corrections for Dave Latham and Carney's sample, even Kepler eclipsing binaries after correcting for the observational selection effects inclinations, show this remarkable factor of 5-6 variation in the close binary fraction with metallicity. Specifically, you get about a factor of 4 variation, a factor of 4 decrease in the close binary fraction as you go to a -1 dex in metallicity to about 0.5 dex. But interestingly, we didn't see any metallicity dependence on the wide binary fraction. So fitting a model to the observations here, this is the period distribution for the different metallicities here. So again, metal poor stars have much larger close binary fraction. Metal rich stars have a lower binary fraction. Here is that Raghavan et al. 2010 distribution. But beyond 200 AU, we actually found that the wide binary fraction is metallicity invariant. And then very quickly thereafter, Kareem El-Badre, Hans Walter Rix used Gaia to confirm that this emergence of this metallicity dependence comes out only below 200 AU. So at 250 AU, there's no metallicity dependence. And then as you look at binaries at shorter and shorter separations, this anti-correlation between the binary fraction and metallicity really pops out, such that even at 75 AU, you're getting this factor of 3 or so anti-correlation between metal poor and metal rich stars. Okay, so what's the theory behind this? What's causing the close binary fraction to decrease with metallicity, but the wide binary fraction is metallicity invariant? Well, we really have to keep in mind the two regimes of binary star formation. On short separations, binaries fragment in this optically thick regime, sometimes via optically thick disks. And so I have this little cartoon here showing the thickness of this optically thick midplane. And as the metallicity decreases, that optically thick midplane becomes geometrically thinner and thinner. And that allows that disk to cool, radiate more efficiently. And so these metal poor disks are actually cooler and thus more likely to undergo disk fragmentation. And so yeah, that was predicted back in 2009, 2014, and finally in 2019 we're able to discover this trend that metal poor solar type stars have a larger close binary fraction. Meanwhile, these wide separation scales are very low densities, this optically thin regime. Like this simulation from Stella, where she actually shows this, the densities here, okay? 10 to the minus 16, 10 to the minus 18, 10 to the minus 20 grams per cubic centimeter. Definitely in this optically thin, low density regime where fragmentation of cores, filaments, does not really depend on the metallicity. And these hydrodynamic simulations here actually show that. They show that the fragmentation on these optically thin cores and filaments is independent of metallicity. In my, according to this timer here, final 7 minutes here, I just want to talk about the impact of binaries on planet formation. Okay, this is a paper from, I guess, 11 years ago now, from Kratter et al. 2012, looking at the disk fraction of different types of stars in a 2 million-year-old Taurus Auriga. So all these stars have the same ages, okay? Roughly the same ages. Single stars have a disk fraction of about 80%, and so do wide binaries. But these closer binaries have a smaller disk fraction. The idea is as the binary separation becomes smaller and smaller, you truncate the radius, mass, and lifetimes of these protostars disks, explain why we see relatively few close binaries with these disks. Over the past few years, VLA and ALMA has really really improved our understanding of protostellar disks, both the gas content, the dust content, and single stars, close binaries, and wide binaries. And what's plotted here, this is a figure from the chapter, is that these close binaries are shifted to the left here in these two diagrams. They have systematically lower dust masses. The protostellar disks in close binaries have lower dust masses compared to single stars and the wide binaries. And the protostellar disks in these closer binaries are also physically smaller than wide binaries or their single star counterparts. Okay, so we see this during the star formation process. The close binaries truncate the dust mass, the gas mass, the size, lifetimes of the disk. And we can see the implications in terms of planet formation. And so this is another meta-analysis of 5 different papers here. We're looking at the occurrence rate of S-type planets, so circumstellar S-type planets, where the planets is orbiting only one of the stars. Sorry, but I'm not going to get to Tatooine-like planets today. We know about 14 or so Tatooine-like planets, but we have hundreds of known of S-type planets. We really can constrain the statistics, and that really enlightens our knowledge of the planet formation process and binaries. And so at wide separations, beyond 100 to 200 AU, I'm calling this suppression factors order of unity. Basically, the occurrence rate of planets in wide binaries is consistent with the occurrence rate in single stars. But as that binary separation decreases, the likelihood of you having a planet around one of those stars decreases dramatically. If you have a 10 AU planet, the occurrence rate of one of the components having a S-type planet, interior planet, is only 15% the occurrence rate that we see in single stars. And what is remarkable is that we see the same trend independent of stellar host mass or planet type and architecture. So this survey was multi-planet systems. Adam Krauss looked at small planets, and Renault was looking only at hot Jupiters, again seeing that same trend. And then most recently, Ziegler et al. Looked at M-dwarf hosts. Again, close M-dwarf binaries suppress planet formation. And so what does this mean in terms of the overall statistics of planet formation around solar-type stars? It means that a third of solar-type stars cannot have planets. And so, again, I'm plotting the overall log normal separation distribution of solar-type binaries. And this wedge here is the fraction, the overall population of solar-type stars that have close binaries that suppress planet formation. Again, about a third of close binaries, a third of solar-type stars cannot host close planets. And that's for a volume-limited survey. For a magnitude-limited survey, you're biased towards these more luminous equal mass twin binaries. This is a Malmquist bias. And for a magnitude-limited sample, the fraction of solar-type stars that do not have close planets is almost half, about 43%. And so we have to account for binary stars when you talk about planet formation and also exoplanet occurrence rates. There's this well-known 3 sigma discrepancy in the hot Jupiter occurrence rates from RV, rate of velocity methods, versus transit surveys like Kepler, TESS, even WASP. RV surveys find that about 1% of solar-type stars have a hot Jupiter. Kepler found that only about 0.5% of solar-type stars have a hot Jupiter. Factor of 2 difference, 3 sigma discrepancy. Similarly, the occurrence rate of Neptunes within 50 days is about 28%, determined from RV surveys. Again, that's about twice what we infer from transiting exoplanet surveys like Kepler. And so we can understand this factor of 2 discrepancy once we account for binaries. The RV surveys for giant planets, they removed spectroscopic binaries from their samples. We're looking for these small amplitude rate of velocity variations due to a potential giant planet. And so they removed any large amplitude variations indicative of a close binary companion. But these close binaries cannot host planets. Perfect. And so by excluding these spectroscopic binaries, they boost their detection efficiency of giant planets by a factor of 1.8, which fully explains the discrepancy in the occurrence rate of RV versus transiting planets. So Lynne just gave me the 1-minute paper there, so I'll go to the key conclusions here. Close, wide, and the overall multiplicity fractions all increase with stellar mass. We think there's at least 4 different dominant formation mechanisms of multiple stars. And the first time with the VLA and ALMA, we have direct observations of core fragmentation, filament fragmentation, that one really cool triple showing disk fragmentation, and also this gas disk-mediated capture. I focus a little bit on close massive binaries. We think, we think they come from disk fragmentation, but we think the majority of binaries come from especially these wide and low mass binaries derived from core and filament fragmentation. Key point that we found out this past decade is multiplicity really depends on environment. The wide binary fraction decreases with age and cluster density, but the close binary fraction decreases with metallicity. And these ALMA surveys have really reveal the differences of these dust disks and gas disks, protostellar disks, between single, close, and wide binaries. And that's telling us that these close binaries really suppress the formation of S-type planets. And again, this is just a few trends here. We're just scratching the surface of this multidimensional parameter space of the occurrence rate and the formation mechanism of binaries as a function of stellar mass, separation, age, etc. And so I think the next decade will explore different corridors of this parameter space, like what is the metallicity dependence of M-dwarf binaries? We talked about the transition of core versus disk fragmentation as a function of mass and separation. But really, where do those transitions occur, and how does it depend on the environment? And how do multiples form in extreme environments, galactic center, globular clusters, dwarf galaxies? Again, I think these are questions I hope we can solve by PP8. So thank you.
You should be expecting multiple questions. Let us start here on the right, this side.
Sorry. I'm Kei Tanaka from Tokyo Tech in Japan, and thank you very much for a great review. And I'd like to ask about the metallicity dependence, but is there any observational constraint for the higher mass or lower mass star formation? I mean, not necessarily the formation, but yeah, multiplicity.
Lower mass M-dwarfs, no. I know of a postdoc working on that. High mass stars, all we have is the SMC and LMC going to SMC is minus 0.7 dex. So far, we don't see any changes in the close binary fraction of massive stars. But the error bars are large and our baseline is pretty small. Again, it's one of those corners of the parameter space we still need to explore. Thank you for that question.
Even for the companion mass? No, the binary fraction is already high for the higher mass, but the companion mass can be.
Oh, in mass ratios, yeah, we haven't even explored that as a function of metallicity. Yeah.
Great. Yeah, thanks.
Okay, someone has discovered a new microphone here in the front.
Hey, JJ Zanezzi, UC Berkeley. So I have a question on your result that you are arguing that close binaries form primarily through disk fragmentation. The expectation is that if they form through inward migration from the disk, is that these binaries should have low eccentricities. But many of the binaries have pretty substantial eccentricities. So how do you reconcile the large eccentricities of close binaries which form through inward migration through the disk?
Yeah, so you can pump up the eccentricity from accretion from a circumbinary disk. There's simulations from Lubo and in the 90s showing how you can change the eccentricity. But I just want to mention that this break between, when we talk about close binaries, solar type and low mass stars are probably coming mostly from core fragmentation. It's really more these more massive close-in binaries that we think come from disk fragmentation migration.
Let's go here.
I'm Simon Goodwin, University of Sheffield. It's always nice to hear about binaries. when you were talking about pre-main sequence binaries, there was a feature in the diagram that you didn't talk about.
Uh-oh. Yeah, there's dragons there. I know exactly. Okay.
Yeah. So the huge excess, by a factor of 2 at sort of tens of AU.
Yeah, 10 to 100 AU. So this measurement, is that your question?
Yeah. Does that worry you? Because it worries me.
Oh my gosh, I've lost sleep over this. So yeah, this goes back to Andrea Guess, 1993, finding this excess at 10 to 100 AU. And it was found in Taurus and Opera Scorpius, and the idea is, okay, maybe only low-density environments have this excess. And then Duchesne et al. 2018 found, oh no, Orion has this excess too. So there's no combination of environments that can reproduce what we observe at 10 to 100 AU. Yeah, that bothers me. I'm a first-year assistant professor, and I have a undergraduate student that will be tackling this problem this summer.
So, any ideas?
I'll talk to you privately, yes.
Okay, in the back.
Hi, Max. This is Johanna Tusky. Nice talk. So I had a question sort of related to this slide. When you were talking about wide versus close binaries, here you're saying wide binaries really care about age and cluster density.
Yep.
But then close binaries really care about metallicity.
Yes.
So does the dependence of binarity on cluster density and age, does that also change with metallicity? So if you're in a lower metallicity environment, are those systems going to care more about these other variables?
Unfortunately, all nearby star-forming regions
okay.
are solar metallicity.
Okay.
Thereabouts. So we don't have the constraint of class 0, class 1, class 2 at different metallicities. Again, another corner of the parameter space that maybe in the next decade we can figure out.
Okay, thank you.
Yeah.
Right here in the middle.
Me? Hi, I'm Suchi Narayanan from the University of Hawaii. Thanks for the great talk. I had a question regarding disk inclination and misalignment with respect to formation mechanisms. And generally, if it's super misaligned, I know that it's turbulent core fragmentation, but we are seeing close in or intermediate binaries with a lot of misalignment. So can you speak to that?
Yeah, so my favorite references are then the Ian Chikala's 2019 paper. And there's a transition of going from more coplanar to then more isotropic distributions. And again, I mentioned we think there's this transition from, at least for solar type stars and solar type binaries and above, this transition from core fragmentation on large scales to maybe disk fragmentations on those sub-AU that form binaries at the sub-AU scales. But where that transition occurs, how gradual or steep it is, don't know. So yeah, I'm not surprised you might be finding some more somewhat compact binaries that are misaligned. Yeah.
Thank you so much.
Okay, I think we have 5 minutes left for questions, and I see more than 5 people lined up, so we may not get to everyone, but let's go here again.
My name is Shigehisa Takaka from Kagoshima University, Japan. My questions are, you said cross-binary suppress formation of S-type planet. But what about the other planet, circumbinary planet?
Yeah, so we still see circumbinary disks. We see circumbinary debris disks. We think that these Tatooine-like circumbinary planets can form readily. So I didn't have time to get to that in this talk, but there's some, at least several dozen references in our chapter, if you want to look at that.
Okay, thank you.
Yep.
Here in the front.
Hi, Max. Great talk. As an exoplanet person, I have to say I'm really
nice. Yeah.
I'm really jealous at how good the binary statistics are. My question is actually, are the statistics that you show, do they go down to the brown dwarf or planetary mass binary for the secondary? And would your results change? Or which results do you think would change if you can go down lower in mass of the secondary?
Yeah, good. That's a good question, and we always ask about observational completeness. For solar type primaries, M-dwarf binaries, yeah, we're pretty complete now to brown dwarf companions. As you go up in mass, we're definitely not finding brown dwarf companions to O stars yet. We don't have that sensitivity. So the marginal mass ratio limitation is around that 0.1, 0.05 in our observational limit. In terms of how that will change the overall fraction, if anything, O stars already have a humongous multiplicity fraction. So if you include these possibly missing extreme mass ratios, it will increase it even more.
Okay, over here.
Hi, Kim Ward-DeWong, Smith College. Thanks so much for this fabulous review. I thought it was really interesting about the disk fragmentation leading to the solar twins and the brown dwarf desert. And I was just curious if this toy model, you're starting with a 200 AU disk, but we know that the circumstellar disks get smaller with primary mass. And I was just curious for the lower mass systems, which might be rare that undergo disk fragmentation, like what effect does that have on the systems like very low mass stars that have smaller disks that fragment?
Yeah, so we don't think protostellar disks that end up forming M dwarfs ever fragment. They're too low in mass to fragment. It's only really around solar type stars and above that we think these disks fragment. And yeah, we counted for that in this toy model where the forming more massive stars likely have larger protostellar disks. But again, that's a factor of a few in size. Whereas here we're talking orders of magnitude in separation. So it's not too important in these toy models.
Okay, thanks.
Okay, let's go here and then in the back.
Okay, Matthew Bate, University of Exeter. You probably can guess what I'm going to say, Max. But just for the other 778
Sure.
people or so, I think generally you've probably overemphasized the importance of disk fragmentation because really exactly how the two objects formed is often hidden by subsequent evolution. So for example, in your toy model with Andrei Tokovinin, whether it formed by disk fragmentation or core fragmentation on small scales, the effects that you're getting are primarily driven by the migration and subsequent accretion. And for example, too, just the multiplicity fraction versus primary mass, a lot of that general picture you can get from dynamical interactions in the sense that low mass stars find it very hard to hang on to companions, whereas high mass stars find it very easy to hold on to companions. So I think just things like accretion, dynamical interactions, those sorts of evolutionary processes often hide exactly the formation mechanism. And I think, you just probably slightly overestimated the importance of disk fragmentation versus just normal core and turbulent fragmentation.
And, these are all fair points, and Matthew and I have had conversations together. And I'll just say, I think it depends on the corner of the parameter space you're talking about. We're talking about a global simulation. Most stars are M dwarfs, and definitely most M dwarf binaries come from, I think all M dwarf binaries probably come from core fragmentation, the subsequent decays you're talking about. Disk fragmentation doesn't play a role in M dwarf binaries. But when you go up in mass, then I think they may play a more important role as indicated by this sharp break and the close binary fraction. I think this is what's really encapturing these two different formation models, is the fact that you get those two trends there.
All right, let's try one more in the back. We may not get to the two other people standing.
Yushen Zhang from University of Virginia. My question here, my question is about the forming mechanisms of binaries. So I'm trying to understand what's the real distinction of the capture and the like a core or filament fragmentation. Like, to me, the capture, like those sources, they form by independent formation events due to the fragmentation of this the clump, and observationally, I feel like along this one system in the early stage or later stage, they may be categorized into different, identified as different core fragmentation or capture. Could you comment on this?
Yeah, so I guess what I meant by capture is these two components probably did form via core fragmentation, but were never initially gravitationally bound. It was only through the subsequent interaction with the gas, or you have a flyby encounter, where they then become gravitationally bound and form a binary in that way. So, yes, the capture scenario requires initial binaries that came from filament or core fragmentation.
So the first two mechanisms, so those are bound at the beginning?
Yes, yeah.
Okay, so, yeah, thank you.
Okay, let's thank our speaker again. I think you still have a triplet of questions to answer.